Fundamental theorem of calculus, day 1. Well, first we found antiderivatives, and then we found area under curves using rectangles and trapezoids. So today we'll make that connection between what an antiderivative has to do with the area under a curve. So I'm going to go through a little bit of theory, so just watch for a moment. So you learned in Algebra 2 probably about sigma notation or summation notation, and recall that what this means is that you would take this lower bound here, this lower limit, and you would plug it into your expression, and then you plug in every integer until you get to that upper limit or upper bound. So it would be 1 plus 3 squared, and then 1 plus 4 squared, 1 plus 5 squared, 1 plus 6 squared, and then the symbol means that you're going to add all those up, and in this case you would end up getting 90. Okay. So let's say that we have this curve, this blue curve here, and we want to find the area under it, or approximate the area under it, and we want to use a bunch of rectangles. So notice how this is labeled. So this is my left bound A, and my right bound B. And I'm calling this value x sub 0, and this is x sub 1, x sub 2, and so on. Over here we've got x sub n. And these are right-hand rectangles. So we went to the right of the rectangle, we go up to the curve, and we top it off. So right-hand rule being used there. So I could say that the area of this first rectangle is going to be f of x sub 1 times delta x. Remember, delta x is going to be the width of the rectangle. And then the second rectangle is going to be f of x sub 2 times delta x. And then the third rectangle will be f of x sub 3 times delta x, and so on and so forth until you have f of x sub n times delta x, okay, where delta x is the width of the rectangle. Well, we can use summation notation to represent this particular sum. We can say that we're going to go from k equals 1 to n of f of x sub k times the delta x, right? Because all of them have a delta x, and then all of them for the height of that rectangle will be f of x sub whatever, okay? So this still is only going to give you an approximate area, and we are really trying to find the true area under the curve. And so if we want to get a more precise value, we need to have more rectangles, and we need to make them very narrow. In fact, what we need to do is take a limit as n approaches infinity. Let me go back to this picture over here. So n is not only like the subscript on that x value, but it's also going to be the number of rectangles you have. So you really want all of these rectangles to be infinitely thin, like thinner than this mark that I'm making with my Apple pencil. And you want to have an infinite number of these rectangles, and that will give you the total true area under the curve. So this, as you can imagine, would be very tedious to figure that out, this limit of the summation notation. Well, we're not going to cover that. Well, what happened is that some mathematicians figured out that there was a relationship between accumulating the area of the rectangles and the antiderivative. And also this particular symbol here, this became this symbol here. And so you can see that the sigma is like a capital S, and then you've got this elongated looking capital S, and then you've got the lower bound on the sigma and the upper bound, and you've got a lower bound, you got the upper bound, and then you have the f of x sub k, which is just going to be f of x, and then you have the dx, or sorry, the delta x, which became dx. So that's where this notation comes from. So the fundamental theorem of calculus, part 1, says that let f be a continuous on a and b, then the integral from a to b of lowercase f of x dx is going to be capital F of b minus capital F of a, where capital F is going to be any antiderivative of f. In other words, capital F prime is equal to lowercase f. If you want, you can write this on your yellow sheet. Now, for number 1, I'm going to walk you through number 1, and then I want you to pause the video and try number 2 on your own. So what we want to do is find the antiderivative of that expression. So the antiderivative of 10x, remember, is going to be 10x squared over 2. And I'm going to do a closed square bracket, and we're going to repeat those bounds there, -4 to 2. So I like to use a square bracket. I've also seen it with just like a vertical bar. Let's simplify that 10x squared. So that's really 5x squared that we're going to evaluate from -2 to 4. Because the fundamental theorem of calculus, again, says you're going to evaluate the upper bound, evaluate the lower bound, and subtract. So I'm going to come back here. I'm going to evaluate the upper bound. That's going to be 5 times 4 squared minus 5 times -2 squared. And when you work that out, you're going to end up getting 60. Let's take a look at the next one. Pause the video and try this one on your own. All right, we're going to do the antiderivative of x squared, which is x cubed over 3, and then the antiderivative of x to the 1/2 is 2/3 x to the 3/2, and we're going to evaluate that from 0 to 1. So plugging in the 1 first. And so this is 1/3 plus, that's basically just 2/3. And that's going to be 0 plus 0. So we're going to get 1. Okay, pause the video and try numbers 3 and 4. Okay, for number 3, I need the antiderivative of 2 secant squared theta, which is 2 tangent theta, that we are going to evaluate from negative pi over 4 to pi over 4. So I'm going to plug in the upper bound. That's going to be 2 times the tangent of pi over 4 minus 2 times the tangent of negative pi over 4. So we need to think about the unit circle. Tangent of pi over 4 is 1, and tangent of negative pi over 4 is negative 1. So we have 2 plus 2, which is 4. And then for number 4, remember, we don't have any sort of like a quotient rule or anything, so we need to simplify this before we can integrate it. So that's going to be, let's call this integral from 4 to 9 of 1 over the square root of t minus the square root of t over the square root of t dt. So that will be the integral from 4 to 9 of t to the negative 1/2 power minus 1 dt. We'll put parentheses here if you like. And then the antiderivative of t to the negative 1/2 will be t to the positive 1/2 divided by a half, which is multiplied by 2, minus t that we evaluate from 4 to 9. Plug in the upper bound, and that's going to work out to be negative 3. Number 5, this one's a little different. We have the graph of g, and we're trying to find the integral from negative 1 to 3 of g prime. Well, we can use the fundamental theorem of calculus, which says that we're going to do the antiderivative of g prime, which would be g of the upper bound minus g of the lower bound. And then we can just look at the diagram, the graph, to find g of 3 and g of negative 1. So g of 3 is going to be 1, and then g of negative 1 is positive 3. So 1 minus 3 is negative 2. Now, for the next one, you might be thinking, well, if we do the fundamental theorem of calculus, then we have to do some sort of antiderivative of lowercase g, which you could call that g of 1, a capital G of 1 minus capital G of 6, but we don't have any way of finding those things. And then you might think, well, maybe I could try to figure out if I have the graph of g, what would the graph of the antiderivative of that look like? But in reality, this really just means the area under the curve, right? So with this one, we can just use geometry. We can do the first, we can switch those bounds, right, with that the opposite property. So it's going to be the opposite of the integral from 1 to 6 of g of x dx. And then looking at the graph, here's 1 and here's 6. So I have like we can maybe divide it up into this rectangle here and then this trapezoid here. So that would be the opposite of a 1 by 3 rectangle plus, and that's going to be 1/2. And then the height of that rectangle, remember that's on its side. So, I mean, the trapezoid, so it's going to be 2. And then one base is 1 and the other base is 3, which is going to end up giving you negative 7. All right, let's take a look at this one. We have the same graph, g of x, and we are doing the integral of from 5 to 6 of g double prime. So let's use first of all, let's split that up. So that's going to be 5 to 6 of g double prime of x dx. Don't forget that dx there. Plus integral from 5 to 6 of just 4 dx. So let's do the fundamental theorem of calculus. This means we're going to do the antiderivative of g double prime, which would be g prime of 6 minus g prime of 5. I'm going to switch colors here. Plus, then here we can just do the regular with the antiderivative of 4, which would be 4x, which we're going to evaluate from 5 to 6. So to find g prime of 6 and g prime of 5, I need to look at the graph, and specifically I'm looking at the slope of the graph, because remember the derivative means slope. So looking at the graph at when x is equal to 5, this slope is 1, and same when x is equal to 6. So g of 6 is going to be 1, g of 5 is also going to be 1, and then over here we can do the antiderivative, so it's going to be evaluate, it's going to be 4 times 6 minus 4 times 5. So that's going to end up being 24 minus 20, so just 4. All right, next, this is a nice question where we have this graph of f prime now, and we're told that f of 0 is negative 3, and the graph of the f prime is given, and we're trying to find f of negative 4. So this can be kind of an intimidating looking question because you have only the graph of f prime and you're trying to find information about the graph of the original function. And nobody's going to want to try to figure out what the graph of the original function is when you're having the graph of f prime, if you can help it. So what we're going to do is use the fundamental theorem of calculus. So we know that we can do the integral from a to b of f prime of x dx is going to be f of b minus f of a. Now, since I have f of 0 and I'm looking for f of negative 4, that's what I'm going to choose for my bounds. So I'm going to say the integral from from negative 4 to 0 of f prime of x dx is going to be f of 0 minus f of negative 4. So f of 0 I have is negative 3, so I'm going to make that substitution there. And I'm ultimately trying to find f of negative 4. So this is this is going to be negative 3 minus f of negative 4. That's what I'm looking for. And then the challenge is, well, could I figure this out? The area under the curve from negative 4 to 0. I certainly could. The area under the curve from negative 4 to 0. So the area that we're looking at would be this sort of sliver here, and then this sort of sliver here. In order to find that, I need to basically do the outer rectangle here, or square, and subtract out the semicircle. So to find the area of that outer rectangle is a 4 by 2, and then we're going to subtract the semicircle, which would be a half of pi times the radius squared, and the radius is 2 squared. So we have 8 minus, well, that's going to become 2 pi, equals negative 3 minus f of negative 4. And I'm trying to find f of negative 4, so I can add this negative 3 over here and divide it all by negative 1. So that's going to become 11 minus 2 pi equals negative f of negative 4. But since I want it to be positive, we're going to just multiply everything by negative 1. Negative 11 plus 2 pi equals positive f of negative 4. Now this one, you can do this a couple of different ways. We have the equation of the derivative function. And similar to the last question, we have f of 1, and we're trying to find f of 3. So we could do something like what we did earlier in the unit, where we could find the antiderivative and then have the plus c, and then use this information to find the c value and then go back and plug in. And that's a perfectly fine way to do it, but I'm going to do this one with the fundamental theorem of calculus. So again, we know the integral from a to b of f prime of x dx is going to be f of b minus f of a. And since I have f of 1 and I'm looking for f of 3, I'm going to use those as my bounds. So the integral from 1 to 3 of f prime of x dx is going to equal f of 3 minus f of 1. So we're going to have, let me just rewrite this. And now we'll just do the antiderivative. So it's going to be x cubed over 3 minus 2x that we can evaluate from 1 to 3. And that's going to be f of 3, which is what we're looking for, minus f of 1, which is negative 2. So let's plug in the upper bound and evaluate. All right, let's go up here. We've got basically 9 minus 6, and then we have a plus 2. So it's going to be 5 minus 1/3 equals f of 3 plus 2. So if I subtract the 2, I've got 3 minus 1/3 equals f of 3. Well, that's 9/3 minus 1/3 is f of 3, getting a common denominator there. So there's 8/3 is equal to f of 3. All right, the last thing I want to talk about is the net change theorem, which is basically the fundamental theorem of calculus. So remember, the area under a rate of change curve gives you the accumulation of change. So you could rewrite your fundamental theorem of calculus. If I wanted to isolate f of b, I can just add the f of a to the other side. And then f of a is your starting amount, and then this is your net change, and that's going to equal your ending amount. Well, here's an example. Let's say that a software company starts the year with 50,000 active subscribers or active users, and their user growth rate over the first 4 months of the year is modeled by this particular function of users per month. So this is a rate function, right? This f of t is a rate function. So the area under this particular curve would give you the total accumulation of change in your users. And they want to know how many users will they have at the end of the 4 months. So we could consider this. We can say that you start with your 50,000, you add your net change from 0 to 4, and that's going to give you whatever f of 4 is. We're not going to calculate it, but again, the idea here is that if you start the year with 50,000, that means that f of 0 would be 50,000. So capital F of 0 would be 50,000. So you're going to see this come up in the future questions with using this starting amount plus your net change is going to give you the ending amount. It's just a reworking of the fundamental theorem of calculus.